Hey guys, and welcome to this second day of 9.1, Parts of Circles. Today as we start, this is information on tangents that we did not get the first day. Happy that you're picking it up here. As we start, just a quick review of some of our terms. So first of all, radius from this picture. To bring it back, pretty obvious that radius would be segment AH or segment FA, and again you can name those forwards or backwards. Chord, one of our new terms. A chord, as you might recall, is a segment that has its endpoints on the circle. Today we have a choice of two possibly, and they're highlighted here, and actually if you look carefully there is a third. This one, which does have another designation, is also a chord. And let's jump to that other idea. That other idea is, of course, diameter, and that happens to be a chord which passes through the center of the circle. Okay, so if I can erase some of this stuff off my picture, we can talk about a couple of other, I guess I started erasing that too. We can talk about a couple of other terms. Tangent line. A tangent line is a line or a segment that touches, and that's the meaning of the Latin root for the word tangent. It means to touch something. This line touches the circle at a single point only. We could also use the word intersect. And point D, the point of tangency is actually point H. It's the name of the point where they cross. So that was one of the answers on your homework you may have missed. And lastly, a new term for us is secant, and that is a line that, or a segment, that touches the circle in two spots like a chord, but it extends beyond the edges of the circle. So the endpoints of the segment, or the pictured line, BD, is a secant because it goes beyond. Notice if we label this falsely, and instead of writing line BD, we write segment BD, we're really talking about a chord. So a couple of differences there you might notice, and this is review from yesterday. Continuing on to today's new stuff, there are a couple of ideas about tangent segments we need to know. So, the tangent segments theorem says, if I have two tangents to a circle from a single point, so again, from the outside of the circle, I have two segments here that are tangent. They may be drawn so they might continue, but the segments we're talking about are DC and DB here. If those are tangent to the circle, as it turns out, then they are congruent. And kind of an interesting way to see this. I think one of the other properties, which we'll review again below, and we'll see it also, is that tangents to a circle happen to be perpendicular to any radiuses. So as we go along and have a look here, we know that there's a right angle corner here, a right angle corner there, and these two segments are equal to each other because they are both radiuses of the same circle. So as it turns out, this four-sided figure actually happens to be a kite. And as part of our definition of a kite, we know that these two remaining sides of the kite are congruent. So anytime we have two tangent segments outside, and we draw in the two radiuses to that point of tangency, and up top, point of tangency, we basically will form a kite. But the meaning today of the big idea is that these two segments, one here and one here, boy, that's a thick highlighter. Those two segments are congruent to each other, which leads to an interesting question. For example, C down below. Find the perimeter of the triangle. And something students often miss in this particular idea is that if BE is 4, which other segment must be 4? BF. If segment EA is 6, which other segment has to be 6? DA. So notice it is not the case that if AB is 10, then BC, the whole side, and the whole side here has to be 10. Right? So watch for that. So in this kind of a picture, watch for tangent segments to a circle. That has to be 7, this has to be 6, and labeling this has to be 4. So now finding the perimeter is a very simple matter. The second idea for tangents, which we talked about, a tangent to a circle is perpendicular to a radius. Now, which particular one? The radius that's drawn to the point of tangent C. In other words, this one here, since B is my tangent point, right, the AD doesn't have anything to do with anything, and any other radius I'd care to think of doesn't have anything to do with anything. It is the one drawn to this point B where it's tangent. That sets up a perpendicular relationship. So, questions they will ask you, something like in example A. If CB is tangent, that's a good thing. That means there's a 90-degree corner. And the triangle that's pictured is actually a right triangle. So for a while we've known Pythagorean theorem, so now we can solve very quickly for the missing AC segment using the Pythagorean theorem. This segment they're asking for, of course, is the hypotenuse, so that is the one that's by itself. When I get the math going, I get c squared equals 89, so c is the square root of 89. Reduce any radicals. Can I factor this and make this 89 a little bit nicer number? Actually, if you look, you will not find any other numbers. So this is indeed our final answer. We cannot simplify that. For example B, it says find DC. So now they want you to find just this little segment here, this piece of AC. Now we've already got AC is the square root of 89. And to find this, notice we should be able to tell something about AD very quickly. AD, of course, is a radius. So if I subtract that radius length from this one, I will definitely get my answer. Since the square root of 89 is 9.433, let's say 34, or 434, can't read my own calculator, and we take 5 away from that, we're going to get 4.434 as I round it. And since they want it to the nearest hundredth, I want to keep that 3. There is a decimal point there. I want to keep that 3, so I check to see should I raise it up to a 4 or keep it at 3. And I need to just keep it at 3. Oops, slip a 4 in front of there. Okay, so that's the types of problems they'll be asking you. And now you have enough information to actually complete practice page 9.1, which you received earlier this week. Thanks. Have a good day. We will see you Friday.